we have been talking about hypothesis testing, and we did it for the proportion, the p-hat, on Friday. So today we're doing it for the mean. So just like we were doing, most of this we're probably going to do on our calculators. But I do want to talk a little bit about this and kind of understanding the t-distribution a little bit, because remember, when we were dealing with the population mean, that's when we had that t-distribution. So that's not the z-table, it's the one behind it, and it was set up a little bit different. So I wanted to practice understanding that table just a touch first. If I'm asking you to find the critical value, I'm asking you to find t in each of these scenarios. So, a right-tailed test, right? So, that means area to the right. That area is 0.025. You have to find the t that matches it. Now, when we look at this table does give us area to the right. Okay, so we're good there. Then, we need to know on this table degrees of freedom. How do we define degrees of freedom?
N minus 1.
So it would be 29 degrees of freedom. So we go down to 29 on our table. Does everybody have it out so we can? And remember the areas are across the top, so we're looking at 0.025. And what is that t value? Who's your formula sheet?
I do. Not that.
Except you need it today.
Yeah, I really do.
All right, so B, if I want the left-tailed test. Now, my table gives me area to the right. So if I'm doing area to the left, what does that tell us about our t?
It's the opposite.
So the t is just going to be the negative. My alpha, so the area here is 0.01. If n equals 7, how many degrees of freedom do we have?
6.
Okay, so I'm looking at 6 degrees of freedom. And I'm going over to 0.01, and I get 3.143. But because it's to the left, it would be negative. Did you guys get both of those? C is two-tailed. Now my alpha is 0.1. But if it's two-tailed, how much will be in each tail? 0.5. You have to divide it by half because it's 10% total, but 5 in each tail. So when I look it up, I'm looking at the 0.05. I know my t values, one will be a negative and one will be a positive, so my t will be a plus and a minus here. How many degrees of freedom?
23.
So I'm looking up 0.05, 23 degrees of freedom, and I get plus and minus
179.
So with our hypothesis testing, there's two ways. With the proportion, I just taught you the p-value approach, finding the probability. If we were doing it by hand with this, that approach is not very good just because the table that we have only has a few of the probabilities on it. So that's the number one reason most of the time we'll do it on the calculator. If we were trying to do it by hand with this one, it would be easier to do the classical approach, which is basically to find the t-value for our data and find the t-value for the scenario and compare them. All right, so we're going to talk through that. The requirements, simple random sample that's independent. The only one I'm actually going to ask you to verify is either it's normal or n's greater than 30. Same criteria we had for the mean before. So anytime I ask you to verify the criteria, either I have to tell you it's normal or the n has to be bigger than 30. And that's the only thing I'll ask you to verify. So first thing, we set our null and alternative hypothesis just like we were doing Friday. The only difference is we're talking about the mean, so we'll do mu instead of the p for the proportion. Then we'll have some alpha level, which will be given. We won't have to make it up. Then we'll find our t-value, which is just like the z. Okay, r value minus the mean divided by the standard deviation. If we were doing it by hand, then basically what we would look at is if our t-value was in the shaded region, we would reject. So on each of these, I was drawing a picture. So if I got a t over here, I would reject. You know, on this one, if my t was right here, would I reject? No. This one, if my t was down here, we would reject. So we kind of looked at that picture and decided. If we're doing it on the calculator, we'll have it find the probability, and then it's the same as before. When you have a probability, you reject when p is less than alpha. So two different approaches to think about it. So this one I do like to kind of talk through the classical approach just to make us understand a little bit more. But the majority of what we will look at calculator in the future. So if I want to test the hypothesis, the mean of the null is 80, and the alternative, the mean is less than 80. We have a simple random sample of n equals 22. Is that big enough?
No.
No, but I said from a population that is normally distributed. So I told us it was normal, so it's okay. All right, so first, compute the test statistic. So that's just like when we were finding z's. Here they call it t sub 0, but we don't, it's just like finding a z. We need our mean and standard deviation for the t distribution. Okay, so think back, you have a couple different ways. This has a formula on it, that's the same one we've done before in chapter, was it 8? So in chapter 8, the very first bullet tells us the mean for x bar is what?
Or equals the mean of population.
Okay, so it's equal to my 76.9. The standard deviation for x bar is what?
P or is it standard deviation over the square root of n?
So the t statistic, basically the t that matches our null hypothesis, is going to be r value minus the mean divided by standard deviation. Oh, I did write down the wrong thing for our mean, didn't I?
It was 80, wasn't it?
Yeah, it was 80. I didn't look back at my, sorry, the 76.9 is our sample. We're looking at the mean for our population. Sorry about that. So our value, 76.9, minus the mean of the population, divided by standard deviation. Negative 1.71. Okay. B, determine the critical value at alpha equals 0.02. So that's what we were doing before. We are testing less than here. So that means the area to the left, because my alternative is less than, is 0.02. How many degrees of freedom would we have?
21.
21. Because it's down here, we know our t is negative. So we look up on our t distribution, 21 degrees of freedom. Alpha is 0.02. And we get so C, I kind of drew my picture on B, but I'll draw it in here. So what this means, this thing is centered around t equals 0. You don't necessarily have to label that, but this is our negative 2.189. That's our critical value. Anything smaller than that, we would reject. Right? What did we get for our t?
-1.7.
Negative 1.7. Is negative 1.7 in this shaded region?
No.
No, the negative 1.7 will be over here. So, this t, that means we fail to reject.
Can we say since t sub 0 is greater than
Yep.
that number?
Yes. So basically, the classical approach is not actually finding the probability, it's comparing the t for our alpha level and the t for our data. If we're in the shaded region, we reject. If we're not, we fail to reject. If we had to do one of these by hand, this would be the best option for it, just because our t table doesn't give us all the probabilities. All right. Ready to look at another one? Assume the resting metabolic rate, RMR, of healthy males in complete silence is 5,710 kilojoules per day. Researchers measured the RMR of 45 healthy males. So what's the 45 telling me?
And
10. Okay. Who were listening to calm classical music and found their mean RMR to be 5,708.07 with a standard deviation of 992.05. At the alpha equals 0.05 level significance, is there evidence to conclude that the mean RMR of males listening to calm classical music is different? So, what do we have to do first?
r is h sub 0, our hypothesis.
Right, we need our hypothesis. So the null is always equal to, we're talking about the mean. So the mean is equal to, what was the basic one?
571.
So the alternative, I want to test if it's different, so that would be not equal. If I am talking about the mean, we should verify our criteria. What criteria do we need?
That is greater than 30.
And we're good there. And that's the only criteria I'll ask you to verify. Okay, so we have two options. We can do this by hand, we can do this on the calculator. Do you guys want me to walk you through another one by hand? No? Just want to talk about how to do it on the calculator? Okay, so what you are going to do is go to Stat, Test. Okay, so Friday we did number 5, the one proportion z test. We are now going to do, since we're talking about the mean involves t, so it's number 2, the t test. All right, now it's going to ask us questions. Are we going to base it off data or stats?
Stats.
Right. Data is if I give you all the original values and you have to enter them into your list. We're going to base it off stats. The mu sub 0 is the mean of the null hypothesis, which is the 5710. X bar is the mean of our sample. What's the mean of our sample?
571. 5708.07.
Okay, S sub x is the standard deviation of our sample, which is
992.0.
N is the size of our sample, which was
40.
okay, and then we have to pick what we're testing, which is not equal. Very helpful to me, especially on like a test, that you write down this so I can tell did you put things in the correct spot in case you make a mistake. So we're testing not equal to calculate. And so it tells me the t, which I don't overly need, but what I really want is p. P, that's our p value or the probability. Okay. This is what I'm looking for.
Why not?
Okay. When do we reject?
If it's smaller than, it's unusual.
We reject if p is less than alpha in general. That's what we kind of worked on Friday. So I look up here, I did give you an alpha level of 0.05. So this is definitely, so since p is bigger than alpha, we fail to reject. This is not unusual at all. In fact, what this means is if the null hypothesis is true, there is a 98.96% chance of getting a sample like I did. So that leads me to believe the null hypothesis is true. Or at least we cannot prove that it's false. Questions there? Let's try another one. According to the United States Mint, quarters weigh 5.67 grams. A researcher is interested in determining whether the state quarters have a weight that is different from 5.67 grams. He randomly selects 18 state quarters, weighs them, and obtains the following data. At the alpha equals 0.05 level, is there evidence to conclude that state quarters have a weight that is different? So we do have to write out the the null and alternative hypotheses every time. What is the null hypothesis?
567.
The mean is equal to 0.567. What's the alternative?
Mean doesn't equal that.
Okay. So this one we would do on our calculator. We are going to enter all of this data into L1. All of your data in L1. We go to our stat, tests, number 2. This time we are going to base it off what?
Yeah.
So you have the option for, not stats, data. We have data and stats. Last one we did data because I listed the mean and everything. Last one we did stats because I listed the mean and everything. But then we're doing data because it's in L1. And so then it asks you, the mean of the null is our 5.67. List should be L1. It's just saying where did you put the data. Frequency should always be set at 1. And then we're testing the not equal. So if we calculate, we should get a t of 2.75, and the probability is 0.0136. So alpha was 0.01. What's my conclusion?
You fell reject. Or is that smaller than?
0.01 is smaller than 0.05. So since p is less than we have evidence to conclude the state orders have a different weight. Any questions there?
What is RD?
He's talking to Alpha. So.
Or,
The alpha
I'm sorry.
is 0.05. Other questions? Okay. Sometimes if we say something has no practical significance, that might mean we reject, but it doesn't really mean much. So I just wanted to show an example of that. So in 2003, the average age of a mother at the time of her first childbirth was 25.2. To determine if the average age has increased, a random sample of 1,200 mothers is taken and is found to have a sample mean age of 25.5 with a standard deviation of 4.8. Determine whether the mean age has increased using an alpha level of 0.05. So what's my null?
2.5.2.
The mean is equal to 25.2. Alternative? Criteria, are we good?
Yep.
Yeah. And it's bigger than 30, so that's good. Okay, so if I'm doing this on the calculator, let's write down what we're typing in so I can check if you make a mistake. We're doing stat, test, number 2. Okay, this time is this data or stats? Okay, so mean of the null is our 25.2. X bar, the mean of the sample we had was
25.
standard deviation of our sample,
4.8.
or number,
1200.
we are testing greater than. So if I select all of that, tells me my T is 2.165. Probability is 0.015. So, what do we do?
So we compare it to alpha.
Is P less than alpha?
Mm. Mm-hmm.
Yeah.
Did you get point? Oh, I did not get that number. I got.
All right.
I got 0.5.
Get 0.5.
Yeah, that's what
You have 25.5 for the mean of your null.
Interesting.
Anyone else get it?
Interesting turn of events here. I was wondering why my T was 0. I thought that was weird.
So, since P is less than alpha, that means reject. There is enough evidence to conclude that the mean age of a mother with her first childbirth has increased. Now, does this mean a lot?
No.
Why?
0.3.
Yeah, we're still talking about a 25-year-old. So is there a big difference between 25.2 years old and 25.5 years old? No, you're still 25. So sometimes we may get that we reject the null, but it doesn't always mean it's some huge result. You know, in this case, it's not practically significant. It's the same age. I'm not going to ever ask you that, I just really wanted you to know if you ever heard that term. Alright, so that is the end of 10.3. Are there any questions? So you guys just have time to work right now while I'm here.